Hello guys, welcome to the session on data structure. So today we'll discuss about some of the data structure based questions. So these are all GATE previous year questions that will be helpful to understand the concept and to place to prepare for interview. Okay, so the first question: the pre-order traversal of binary search tree. The pre-order traversal of binary search tree, the 15, 10, 12, 11, 20, 18, 16 and 19. So this is the pre-order traversal tree of binary search tree. So which one of the following is a post order traversal of the tree? So these are the options they are given, and this question is asked in the GATE 2020. So the correct answer is, so this one, the 11, 12. So let us see how we got this answer. So the pre-order traversal of binary search tree, so that they are given. So this tree, that the nodes they are given, and for this pre-order traversal tree, pre-order means, so just I'll take the, I will explain with the paste. Okay. Right. So they are given the pre-order traversal tree. So this is the value they are given, and so pre-order. So as you know, pre-order, pre-order. So that is root node, then left, then right, right, left node, right node. So that is pre-order, and in case of the in order means the left root node, then right node. So that is in order. And in case of the post order, in case of post order means left right node, then comes the root. Okay, so here they are given this particular pre-order traversal. So pre-order traversal means here the first comes the root. Okay, so here we can we know that here the first node is the, so the first node is the root node. Okay, so root is 15. So in the post order, the last node is in this post order, the last node is the root. So in the post order sequence, the 15 must be at the last. 15 must be at the last. So here the options they are given B and D, where we are having the 15 is at the last place, last position. So in post order, the last node is the root, so the post order sequence 15 must be at the last. Okay, so how we can solve this one? Yeah, I will just copy that. wait. Okay, so this is the data. It is not responding. Right. So text vertical. Okay, so this is pre-order traversal tree. So what to do? So here what we can do is, oh shit, means pre-order they are given, and with this we can draw the post order. So the text, yeah, yes, okay. Then I'll take a pen. Okay, it's giving error. First I'll save this one. Okay, so it is giving the error. Let me use paint. Okay, so here what we can do is, so this is pre-order they are given, right? And we know this is the pre-order and we know the root is 15, right? The root is 15. Okay, so let us take that number, and so here like root is 15, so the less than 15, the less than 15 means the right. So here pre-order here after the 15, the numbers like nodes 10, 12, 15. Okay, so 15 is the root, right? 15 is the, this is the root, and the numbers, the nodes 10, 12, 11. So these are the, that comes in the left side because it's a less than the 15, and the nodes 20, 18, 16 and 19. So these are the nodes that comes at the right side. Okay, so next, so in the pre-order, the this next node, so that is this particular, the 10 will be now here act as a root node, and for this just check it out, the number that is less than 10 and So here both the numbers, the 12 and 11, both are greater than 10, so that comes at the right side. And here also the first node, the 20, is act as a root node, and just check the number that are greater than 20 or less than. So here these three numbers 18, 16 and 19, these are all the less than the 20. Okay, so here next this 12 will be the root node, and just check less than or greater than. So 11 is the less than, so this is the root. Okay, then 20. Okay, so this we covered. Then yeah, so we need to cut 12 and 11. So after that 20 will come. Okay, then 20, then 18. 18 will be the root node. Then just check the nodes that are less than. 16 is the less than 18 and 19 is the greater than. So then next is this root, that is the root node, and 19. Okay, so in this way it is forming the tree. So here just I will erase these values. Now you will get clear idea. Okay, so with the pre-order they are given, we draw the post order, right? Okay, now what to do? You have to draw the post order. So post order means just the one simple trick I can tell you. So for pre-order, in order, then post order. Okay, post order. So one simple trick is that, suppose this is the root node, right? Okay, so which one is the root node? 15. Okay, right? So in the 15, so here you have to start from the root node, and it is visiting first time in the, that is 15. So here write down first time visiting the 15. Then here just you continue with the, so again it is visiting first time the second, that is node, that is 10. Okay, first time. So here there is no leaves, so second time it is visiting first time to the, then again it is come back here, it is visiting the second time. So second time means you just mention in the in order here. It's a first time visit, second time in order, third time in post order. So come here, 12 node visiting first time. So 12 node visiting first time. Then comes here, okay, so 11 node 11 visiting first time. So here you can write the leaves, means if there is no leaves for a node, you can just write like this. Okay, so 11 for first time, then comes here, then second time for the 11 visiting tree traversal. Okay, third time it is visiting to 11, so just write down here. So then comes here second time again, second time again to 12 node, the node 12. Okay, then comes here down, third time to post order, right? 1 to third time it is visiting to the node 12, third time to the node 10. Okay, then comes here, okay, second time to the node 15. So just keep in mind the first time visit, second time visit, then third time visit in the post order traversal. So here the first time it is visiting to the node 20. Okay, then comes here 18, first time visit, then it comes down 16, the first time visit to the node 16. Okay, okay, so first time, then second time to the 16, then again here it will come third time visit to the 16, then here it is second time to the 18, the node second time 18, then first time to the node 19. Okay, so first time to the node, second time to the node 19, node visit, then third time to the node 19, then it comes to third time to 18 node visit, then second time to 20 node, then comes third time to 20th node, then third time to 15, right? So this is your the tree traversal: pre-order, in order, and post order. So whenever you visit the first time, so that comes in the pre-order, second time in order, and post order third time. So I hope you understood this concept. So this is the they are asked the post order. So just to go through the slide. Okay, so option 11, 12, 11, 12, 10, 16, 19, 18, 20, 20, and 15. Okay, so this is the way how we can draw the post order from a given pre-order. Okay, so finally we will get this particular answer: 11, 12, 10, 16, 19, 18, 20, and 15 as a post order. Okay, see, this is also the way the root node, and the less than 15 will come, that is in the pre-order sequence 10, 11, 12, and here the right side 16, 18, 19, 20. So here the 10 is the root node, and the 11 and 12 are the greater than 10, so that comes the right side. And here the 20 is the root, so 16, 18, 19 are comes in the left side, because it is less than. Again here 12 is the root node. Okay, so 11 will come at the left side. So in this way we have to find the post order. So this is also the other way, greater than, less than. Okay, so the final answer it is same way whatever we are drawn, but just keep in mind that tricks. So the first times visit means pre-order, second time visit in order, third time post order. Okay, So next question, consider a double hashing scheme. Consider a double hashing scheme in which the primary hash function h1 of k is equal to k mod 3 h1, this is the hash function k mod 23, and the secondary hash function is h2 of k is equal to 1 plus k mod 19. So assume that the table size is 23. Assume that the table size is 23. Then the address written by the probe 1 in the probe sequence, assume that the probe sequence begins at the probe 0 for a key value k is equal to 19 is. So the key value they are given, so that is k is equal to 90 and the size is 23, the table size. So here the probe sequence in the list location which a method for open addressing that produces as alternatives in case of collisions. So the k value they are provided, the probe. Okay, so here the key value that k is 19 and the hash functions h1 of k is equal to k mod 23. So that is 90 mod 3 means we will get the 21. And in case of collision we need to use secondary hash function, so that is h2 of k is equal to 1 plus k mod 19. So 1 plus k, the key value is 90, 90 mod 19, so 1 plus 14, here this 90 mod 19 will get 14. Okay, so that is 15. Okay, so now this 21 from the first hash function and secondary hash function 15 mod 23, so that is 36 mod 23, and here you will get the 13, that mod this value is at 13. Okay, so the address is 13. The probe sequence begins at 0 for key value 19. The what is the address? Address is 13. Okay, address is we get 13. The next question, what is the worst case time complexity for of inserting the n elements into an empty linked list? There is a empty linked list. If the linked list needs to be maintained in the sorted order, if the linked list empty linked lists needs to be maintained in a sorted order, so the question is ambiguous, so it needs to be maintained in a sorted order. So there are two possible cases. It needs to be maintained in a sorted order on each step after the each insertion. So when we are inserting an element into the empty linked list, okay, empty linked list, and to perform the sorted order, the list of every element will take O of n square. Okay, in a empty linked list for every element it will take O of n square. So each insertion it is n square, O of n square. So each insertion into the sorted linked list will take O. It will take the insertion into the sorted list. It will take O of n, and since the total cost for n operation is O of n square, for each insertion into the sorted linked list it will take theta of n, but the overall cost it will take theta of n square. So it needs to be maintained in sorted order on the final step only after all insertion. It needs to be maintained in sorted order only after the all insertion. So when we are inserting all elements into the empty linked list, and to perform a sorted list using the merge sort, so after inserting all the elements, after the inserting all the elements will take O of n log n time, O of n log n time, O of n log n time. So for insertion of elements, so insertion of elements into the sorted list, it will take O of n, and the total cost will be theta of n square, and here it needs to be maintained in the sorted order on the final step only after all the insertion. Okay, so when we are inserting all the elements into the empty linked list and to perform a sorted list using the merge sort, so after inserting all the elements, it will take O of n log n. So this O of n log n time. So that is the means here they are given that both the options are correct, but in officially they are mentioned O of n square, the correct answer. But if we see both, means inserting the n element into empty linked list, if needs to be maintained in a sorted order. Okay, so it will come the first one when we perform the sorted order. After for every element it will take O of n square, and for total cost it will take O of n square. And here means after inserting all the elements, and if we use merge sort to sort, then O of n log n time, that is worst case time. Okay, consider one more example. Next, consider the following C program. So that includes, it's a array E. Okay, two-dimensional array 1 2 3 4 5 6 7 8 9 10. So the array they are given printf a plus star a plus 2 plus 3, the output of the program. So here, so a they are given a two-dimensional array, right? So here the a is the address of 0th index. So here, so the array, the again they are given 1 2 3 4 5 the values 1 2 3 4 5 6 7 8 9 11 12 13 14 15 16 17 18 19 20. So the a is a two-dimensional array. A is the address of 0th index in the one-dimensional array. So the star a that indicates address of the 0th index element of 0th index in the one-dimensional array. 0th index element. Double star a means the value of the 0th index element of the 0th index one-dimensional array, the value. So here the double star a means it indicate the value 1, this one. Here they are asked about this printf, this statement. Okay, so star a means that gives the address of the 0th index element. Star a, the address of the 0th index element of 0th index one-dimensional array. And double star a means it gives the value of that the 0th index element in a one-dimensional array. So double star a means 1. And here they asked about double star a plus 2. So a plus 2 means the value is double star a means 1. So 1 plus 2, that is 3. 1 plus 2 is 3, and double star a means 1 plus 2. So they asked about this. First we are taking this one, double star a plus 2. So double star a means 1 plus 2, so that is 3. So the a plus 3, so that is the address of the third index element, address of the third index in a one-dimensional array. A is the 0th index. Now the a of 3 a of 3, so that is the means here we got this value, right? Now we found this one, double star a plus 2, so that is the value is 3. Now here we are having a plus 3, so a plus 3 is the address of the third index in the one dimensional array. Okay, so star a plus 3 means the address of the 0th index element of third index in the one dimensional array, and star a plus 3 plus 3, so this star a plus 3 plus 3 here, this one, so that is the third index element of third index one dimensional array, third index element of third index one dimensional array. So that is this one, 19. So 19 we are getting. Okay, third, the value of star means the here we will get address, star a plus 3 plus 3 means the address of the third index element of third index one dimensional array. Okay, so double star, here we have up to this first star means we will get the address, and the second star means we will get the value. So value of the third index element of the third index one dimensional array, so that is 19 here. Okay, the 19. Okay, so the output of the program will be 19. Output of the program will be 19. Okay, next, what is the worst case time complexity of inserting n square elements into an ABL tree with n elements initially? Inserting n square elements. So the for worst case, so the answer is here, the okay, theta of n square log n. The first insertion time complexity will be, the insertion time complexity in this ABL tree is O of log n, O of log n. The second insertion of the time complexity O of log n plus 1, O of log n plus 1, second element insertion time complexity. So the time complexity will be O of log n plus O of log of n plus 1 to for nth element O of log of n plus n square. So this we can written as O of log of n into n plus 1 plus n plus 2. So here we will get log of n square. So that we can written as O of n square log n, O of n square log n for n elements. So AVL is there which with n elements, AVL tree with n elements. Now inserting n square in that tree, so each element that take O of log n times, so the total time will be O of n square log n, O of n square log n. AVL tree that all operations insert, delete, search, that will take O of log n time. So in question they asked about n square element. The worst case it will take is big O of n square log n time. Okay. Next question. In a balanced binary search tree with n elements, what is the worst case time complexity of reporting all the elements? Worst case time complexity of reporting all elements in the range a comma b. In the range a comma b, assume that the number of reported element is k. In a balanced binary search tree with n elements, what is the worst case time complexity of reporting all elements in the range a comma b? Assume that the number of reported elements is k. Okay, so first you will have to check if the elements a and b, so here there is some mistake, so here it is only a and b are present in the binary search tree or not. since the binary, so just to make a note here, this is only A and B. Since the binary search is balanced, it will take theta of log square n, theta of log square n time for that. So here it will be 2. Okay, so the traversing k elements, that would take additionally theta of k times. So the correct answer is theta of log n plus k, theta of log n plus k. So that is this one, second, theta of log n plus k, assuming it is taking some extra elements. So the B option, theta of log of n plus k. So if you consider this one more example, if a heap has 1023 elements, if a heap, okay, so this is the log of n plus k. If a heap has 1023 elements and it will contain 5 tall leaves, and since it is a min heap, the maximum will be present in the leaves. So assume it is not, then there will be some elements present under it, and this will violate a min heap property. So here, so this is the the 5 tall leaves. So 1 2, okay, so this is the levels of the leaves, 1 2 4 8 16 up to 5 tall leaves. So if you have n elements in the array, we know that to find the maximum it takes n minus 1 comparison. So in this case there are n is equal to 5 tall, so the answer should be 511 for finding maximum minimum. Okay, 511 will come, 511. So here there is one more on traversal tree question. So post order, the post order they are given in order, post order and in order. I think some question slide is missing here. So just I can assume that it's a post order is given, and in order, okay, means with the post order they are drawn the in order, right? So here just I will take this value and I will draw it here. Okay, right. So the post order they are given, this is the post order. So post order means left right and root node and the root node. So here one is the root node, right? So the in order, so in order we have to draw. So here so this I will take here. The in order for this is, so this is the root node, one is the root, so the left and right subtrees, So here it comes whatever the left side part. Okay, the in order. The question, yeah, we'll try this later. The next question, a queue is implemented using the non-circular linked list. It is a linked list, non-circular. The queue has a head pointer and a tail pointer. So let n denotes the number of nodes in the queue. N denotes the number of nodes in the queue, and let nq be implemented by inserting a new node at the head. Nq is implemented by inserting a new node at the head, and dq is implemented by deleting a node at the tail. So which one of the following is the time complexity of most time efficient implementation of nq and dq respectively for this data structure? So here the time complexity, here it will come this theta of n, theta of n for insertion and deletion, because here it is a non-circular linked list, and here nq at one end is performing and dq at the another end. So for insertion of a node at the beginning of the linked list only need the manipulation of the pointer. So theta of 1. If we have a pointer to the tail of the list, in order to delete it, we need address of the second last node. If you delete, we need a second last node, the address of second last node, which can be obtained by traversing the list. So which takes the O of n time. So here in this NQ and DQ operations are performed in different manner. So NQ is done at the head and DQ is done at the tail. So to NQ, create a new pointer to make a new node, and it takes for new pointer it points to O of n, and for DQ it takes theta of n, that is O of n. Okay, so here the option will be okay, for NQ it is taking O of 1 DQ O of n time. So here this one B, I think B will come. Okay, for NQ we are taking O of n, O of 1, and for DQ O of n, O of n. So our option is B. For NQ we are taking the O of 1. The insertion in the beginning of the linked list only need manipulation of the pointers beginning. So that is O of 1 time, and for deleting for DQ at tail of the list, we need the address of that second last node, because we are deleting here. So takes O of n, O of n. So O of 1 and O of n. Option is B. Then the next question, let G be the simple undirected graph. G be the simple undirected graph. Let TD be the depth first search tree. Depth first search tree of G. Let TB be the breadth first. TB be the breadth first search tree of the graph. Consider the following statements. Okay, so for undirected graph, TD is the depth first search tree, TBB the breadth first tree, breadth first search tree of the graph G. Consider the following statements. So here, which of the statement we need to consider? So no edge of G is cross edge with respect to TD. No edge of graph G is cross edge with respect to the depth first search tree. A cross edge is a G cross edge G in a graph between the two nodes, neither of which is ancestor of the other in the TD. For every edge u comma v of graph, if u is at the depth I and v is at the depth j in the breadth per search tree, then I minus j is 1. So which of the statement above is true? So here there is no edge in the graph that cross edge with respect to the depth first tree. So that is only the first statement is true. In undirected graph, they do not have the cross edge in the depth first search tree. They do not have the cross edge in the depth first search tree, but can have the cross edge in the directed graph. But here they are given as undirected graph. So hence the first one is true. So just draw a single ABC where source is A, vertex B and C are at the same level of distance 1. Okay, here the edge classification in the depth first tree. For undirected graph, so there is no edge. For directed graph, there is a tree edge, then there is a back edge and forward edge. So in case of the depth first tree, but in case of undirected graph, there is a tree edge and back edge, and there is no cross edge. There is no cross edge, but in the directed graph of depth first tree, so there is a cross edge. Here the cross edge. In binary search, in the breadth first search tree, the edge classification in directed graph tree edge, back edge, and cross edge. But in the undirected graph, there is a tree edge and cross edge for the breadth first search. Okay, for depth first search for undirected, there is no cross edge, but for the breadth first search tree, there is a cross edge for the undirected graph. For both directed and undirected graph, we have the cross edge. The next question, the number of possible min heaps containing each value, each value from 1 to 7, that exactly once is, so that is 80. The possible min heaps in a value from 1 to 7 is 80. So here we have the 7 distinct integers and sort it. So after sorting, pick the minimum element and make it a root in the minimum hop. So here only one way to make a root in the minimum heap. So we are left with the 6 elements. So one element is the root, and we are left with the 6 elements out of 7. So the total way to design min heap from the 6 element is C6 comma 3 into 2 factorial 2 into, so here we'll get like this, C3 comma 3 into 2 factorial. So that is here picking up this any 3 element from the left subtree, and each left subtree combination can be permuted in a 2 factorial ways by interchanging the children's. Okay, three elements in the elements for the left subtree. So we will get 80. So for any two mini heaps, here this is the one element we taken as a root. So for left three elements, the left sub tree, we can always directly fix them only to the left and one to the right. So problem is reduced by creating a two sets of mini heaps. So that is 6c3 into 2 factorial ways. Means there are select three elements from the six elements and form a mini heap at the left subtree. Select the three elements out of the six elements. So 6c3 into 2 factorial ways. Okay, so remaining three elements go to the right and they can form the a 2 factorial mini heap. Okay, so total mini heap is 6c3 into 2 factorial into 2 factorial. So 6 into 5 into 4 divided by 3, 2 into 1 into 2, 2. Okay, so here we will get 20 into 4, that is 80. 80 is the correct answer. 80. Okay, so consider the C code fragment code below. So this is the code, integers, then node pointer, next join node mn node pointer, the next. Okay, so assuming that m and n point to a valid null, m and n that points to valid null terminated linked list, invocation of join will be. So these are the options: append the list m to the end of the list, n for all inputs, either cause a null pointer dereference or append the list m to the end of the list n, cause a null pointer dereference for all inputs, append list n to the end of list m for all inputs. So the correct answer is either cause a null pointer dereference or append the list m to the end of the list n, append the list m to the end of the list n. Assuming here that m and n points are valid null terminated linked lists. So the correct answer is either cause a null pointer dereference or append the list m to the end of the list n, append the list m to the end of the list n. So as specified in the question, that m and n are the valid lists, but there is no specific condition or statement that tells the lists are empty or not. So we have to consider both the cases. The lists are not null. The lists are not null. So invocation of join will append the list m to the end of the list n. So m is equal to 1, 2, 3, n 4, 5, 6. So after join it becomes 4, 5, 6, 1, 2, 3 null. Okay. If the lists are null, if the list is n is empty and itself null, then joining and referencing would obviously create a null pointer issue. So it may either cause a null pointer dereference or appending the list m to the list at the end of the list en. Okay. So either it may cause a null pointer dereference or append the list m to the end of the list en. Okay. So next question, let T be a tree with 10 vertices. There are 10 vertices. The sum of the degree of all vertices in T is the sum of degree. There are 10 vertices. The sum of degree of all vertices. Sum of degree of all vertices in the T, in this particular T, is sum of degree of all the vertices is 18. How? So the sum of degree of all the vertices is double the number of edges. The sum of degree of all the vertices is the double of the number of edges. So a tree with 10 vertices that contain the n minus 1 edges. A tree tree with 10 vertices that consist of the n minus 1 edges. So 10 is the number of vertices, 10 minus 1 9, 9 is the edges. So the sum of the degrees of all the vertices is 2 into number of edges. Okay, so they are given the number of vertices, so from that we got the edges, so that is n minus 1. So that is 10 minus 1, 9 edges. So sum of the degrees of all the vertices, sum of degree of all the vertices is, it is the double the number of edges, double the number. So 9 into 2, that is 18. So 9 into 2 is 18, means it double the number of vertices. Sum of degree of all the vertices is the double the number of edges. Next question, a circular queue has been implemented using a singly linked list where each node that consists of a value and a single pointer pointing to the single pointer that is pointing to the next node. So we maintain the exactly two external pointers. We maintain exactly the two external pointers, that is the front and rear, pointing to the front node and rear node of the queue. Which of the following statement is correct for such a circular queue so that the insertion deletion operation can be performed in a O of one time? Okay, in a circular queue that has been implemented using singly linked list where the each node that consisting of value and a single pointer that is pointing to the next node. So we maintain the exactly two external points, that is front and rear pointing to the front node, rear node of the queue. So which of the following statement are clear for this correct for this circular queue so that insertion deletion operations can be performed in O of one time? So the options is the next pointer of front node points to the rear node. So in O of one time means the second is correct. The next pointer of rear node in a circular queue, the next pointer of the rear node that points to the front node. The next pointer, the rear node that points to the front node. So second is correct. Okay, the rear node it points to the front node. The next pointer of this rear node it is point to front node. So the second is correct. If we consider the circular linked list, the next node of 44 is 11. So if you place the pointer of next front node, that is 11, to reach to the 44, then we have to traverse the entire list. So for delete in O of 1 and for insertion O of n, it is clearly known that the next pointer of rear node to the front node, hence only 2 is, because here they are asked which one is correct for a circular, so the insertion deletion operation that way can be performed in O of one time. In O of one time means here the rear node that points to the front node. Okay, so second is true. The breadth first search algorithm has been implemented using a queue data structure. So one possible order of visiting the nodes of the following graph. Breadth first search that is implemented using the queue. So that is queue means first in first out. So what is the one of the possible order visiting the nodes of the following graph? So the correct is Q, M, N, P, R, O. Just discuss it here. So here the first option MNOPQR. If you try to run the breadth first search, after the M you must traverse NQR. After the M you must traverse NQR in some order. So here P is traversed before the Q. P is traversed, that is before Q, so which is wrong. And in NQMPR, this is also the not breadth first search. P is traversed before the O. P is traversed, that is before the O. Before the O. QMNPRO, that is correct. So this fourth option is also incorrect, as R needs to be traversed before O. This R needs to be traversed before O. Okay, R needs to be traversed, that is before O. So for breadth first search algorithm, QMN PRO. So R needs to be traversed before O. So the option the first option cannot be a breadth first, as a traversal starts with M, but O is visited before the N and Q. O is visited before the N and Q. In breadth first search, all the adjacent must be visited. The adjacent must be visited before the adjacent of adjacent. All the adjacent must be visited. M, N, O, P, Q, R. So here O is visited before the N and Q. All the adjacent must be visited in the breadth first. So option B, NQ MPRO, it cannot be breadth first search, because here P is visited before the O. P is visited NQM. Okay, NQM POR means here in the second option P is visited before the O. P is visited the adjacent node before the O, before the R, before O. Okay, so C and D match up to QMNP QMNP, the adjacent nodes. QMNP, because M comes before the NP, because R is M's neighbor. R is M's neighbor, so it gets added to the Q before the neighbor of N and P. So thus R is visited before the O. R is visited before the O. So the correct answer is third one. Okay, so let us consider a pre-order traversal of the binary search tree. They are given. Then post-order traversal of the tree. So you need to find out the post order. So pre-order means here the root, left and right node, right? So the 12 is the root. So in pre-order 12 means in the post order where you will get at the last. So out of the, so first is eliminated, so then next three you will get the correct option. So here, so from this pre-order how we can get the post order? So the root is 12, and here you have to uh, find out the less than the 12 elements. So less than 12, 8, 6, 2, 7, 9, 10, then 16, 15. Okay, then here the next, here the after the root, what is the next? 8. That is the act as a root. Okay, so shall I discuss with taking in a paint? Okay, better I will go with okay. So this is the pre-order. Okay, so in this pre-order, so in the pre-order, so this is the root node. Okay, so 12, and just find out what is the less than 12. So less than 12 means 8, 6, 2, 7, 9, 10. So these are the elements that comes in the less than 12. Sorry. Okay, 12. So I will take these elements here, and these are the greater than 12. Okay, greater than 12. So this is the root, this is the left, right subtree. Then take the next element after the root, so that is 8. So now 8 is the root. Okay, and for this left and right, so 8 is the root now. Okay, so for 8 is the root, so the less thans are 6, 2, 7. These are the less elements, and 9 and 10 are greater than the 8. Okay, next comes the element 6. So 6 is now root, 2 is the less than 6, 7. So 2, now 2 is the root. Okay, so I'll write it properly. 2 is the root. Then next take the 7. So the 7 is the root. Okay, then take 9. So 9 is the root. So here the 10 is the 10 is the next take 10 is the greater than the 9. So it comes at the right side, right? Then take 16. So 16 is the root. Okay, this is the right side of the tree. Then this is the root now. Okay, so 16 out of these elements, 16 is the root. So here the less than 16s are 15, 19, 17, 20. These are the elements that come at the right side. Okay, take the 15. So this is the left side, the root. Then 19. So here it is comes the element root. Then take 17. 17 means it comes at the left side, and 20 comes at the right side, right? So this is the how the tree comes. So here now we have to draw the, yeah, just I will make okay, so now you have to draw the post order of this particular tree. So as I already told, pre-order they are given. Pre-order means 1 widget, in order 2 widget, 3 widget. Okay, if there is a 3 order, means 3 times widget you have to check, as initially I have discussed about this in the start of the video. So now what is the question is about the post order, right? Post order means 3 times widget. So here just better I'll just connect it properly. So use the rubber to, so these are the some elements that I'm remove. Okay, means otherwise you'll get confusion. So this that tree. Okay, then here I will write you should have the leaves. Okay, here also this. Okay, so for post order travels, the root is here, this one. 1 visiting, so say this is also visiting. 8 is 1 times, 6 1 time, 2 is 1 time, second time, and here third time. So third time is take note down 2, then the travels are here, it will go. Second time the 6 is visiting, 7 1 time, second time 7, third time the 7 node is visiting, then this will come the third time 6 is visiting, then here it will second time 8, first time 9, second time 9, first time 10, second time 10, third time 10, then it will go here the third time 9, and this particular node is visiting third times, second time 8, first time 12, first time 12, right? So here 12 means here, yeah, 12 is the root, no, yeah, 12 is the root. First time it is, second time visiting 12, first time 16, 15 first time, second time, third time 15. Then this will go like this, second time 16, first time 19, first time 17, second time 17, and third time 17. Third time 17, here second time, first time, second time, third time 20. No, 20 third time, then 19 third time, 16, then third time 12. So this is the how we get the post tree. Just check it out. Just separating the elements. So the correct 276, 10 9 8 15 17 20 19 16 2. So this is the how we get. Okay, so next question. A queue is implemented by using an array such that NQ and DQ operations are performed efficiently. NQ and DQ operations are performed efficiently. Which one of the following statement is correct? So the n refers to the number of items in the queue. So here the queue is implemented using array such that NQ and DQ operations are operations performed efficiently. So which one of the following statement true? Both operations can be performed in O of one time. Both NQ DQ are performed at one O of one time. At most one operation can be performed O of one time, but worst case time for the other operation will be sigma of n. The worst case time complexity for both the operation is sigma of n. The worst case time complexity of both the operation will be sigma of log n. So what they are asked about, which following statement is true? True for, okay, so the correct option is the both the operations that are performed in O of one time, because here they are performing NQ and DQ operations are efficiently. Efficiently means it comes O of one time. Since they are mentioned in the questions, both the operations are performed efficiently, so the hence even in the worst case time complexity also, even worst case time complexity also O of 1, because they are used the word efficient. So use the circular queue there, and it won't be any need of shifting in the circular in the array. Okay, use the circular queue. So the option is correct, O of 1. Then consider a following directed graph. Consider this directed graph. The number of different topological ordering of the vertices of the graph is, okay. So the correct is here, it is some mistake is there option. So the number of different topological ordering of the vertices is 6. The different topological ordering of the vertices, it is observed that A is starting from the vertex and F is the final one. Also observe that C that comes after the B and E. After the C must comes after the B and E, and E must come after the D. E must come after the D. So the topological ordering, okay. C that must comes after the B and E, and E must comes after the D. So A, B, D, then B to C and D, the topological order, okay. Then here A, B, D, okay, means we need to reach from A to F. So here D to C and E, C to E, E to C. So there are total 6 topological ordering. 6 topological ordering. The next question, let G be a weighted connected graph, weighted undirected graph with distinct positive edge weights. If every edge weight is increased by same value, then which of the following statements are true? P, the minimum spanning tree of graph G does not change. Q is the shortest path between any pair of the vertices that does not change. Shortest path between any pair of vertices that does not change. So for a weighted undirected graph with distinct positive edges weights, if every edge weight is increased by the same value, edge weight is increased by the same value, so which of the following statements are true? For minimum spanning tree, the G does not change, and the shortest path between any pair of the vertices that does not change. The correct answer is only the P, that is minimum spanning tree of the G, minimum spanning tree, the graph, it does not change, but here it will affect on the Q, okay. So the correct option is P. For the undirected graph, weighted graph with distinct positive edges, so every edge weight is increased by the same value. Suppose here A, B, C, if the every edge value, if it is increased by 2, so 3, 6 and 4. In minimum spanning tree, it will not change the ABC in both the cases, but in shortest path will change, because in the first figure the path from A to C is 4, is calculated by the ABC, but in figure 2, the AC is the direct path. AC is the direct path. The next question, an operator delete I for binary heap data structure that is to be designed to delete the item in the ith node. To delete the item in the ith node, assume that heap is implemented in an array. Heap is implemented in an array, and I refers to the ith index of the array. If the heap tree has depth d, that is number of edges on the path from root to the farthest leaf, the number of edges from the path from the root to the farthest leaf, then what is the time complexity to refix the heap efficiently after the removal of the element? So an operator delete for a binary heap data structure is to be designed to delete the item in the ith node. Assume that the heap is implemented in an array, and I refers to the ith index of the array. And if the heap tree has a depth d, that is number of edges on the path from the root to the farthest leaf, then what is the time complexity? What is the time complexity to refix the heap efficiently after the removal of the element? So the correct answer for this is O of D, but not O of 1, but not the O of 1. Means here the time complexity to refix the heap efficiently after the removal of the element. So that is O of D, but not the O of 1. If the heap has n elements, generally it takes O of n elements to delete an arbitrary element for n elements, O of n. but we need to find that element in O of n time. So delete the element, the O of height. So deleting involves swapping the particular element rightmost leap and do the heapify on that node. But here we won't need to find that element because the delete in the index, and delete of I is the index of that element. So delete time O of height is equal to O of D. So here we are deleting the element with the index, so O of height is O of D. Okay, so O of D but not O of 1. So the correct option is second one, O of D. O of D. So consider a weighted undirected graph with four vertices, for undirected graph where the weight of the edge I comma j, the weight of the edge I comma j is given by the entry, the weight ij in the matrix W. So the largest possible integer value of x for which at least one shortest path between some pair of vertices will contain the edge with the weight x is given. The largest possible integer value of the x. So here the largest value of the integer x for which at least one shortest path between the some pair of vertices will contain the edge with weight x. So here the correct answer is 12. The correct answer is 12. The largest possible integer value of x for which at least one shortest path between the some pair of vertices that will contain the edge with weight x. So let the ABCD. So here they are given the four vertices with the edge. So ABCD. So here A to A 0. There is weight is 0. A to B 2. A to C 8, A to D is 5. Then B to A is 2, B to B 0, B to C is 5, B to C is 5, B to D is 8. So in this way, let X connect C and D. The shortest path excluding the X from C to D of weight 12 is CB A D. The shortest path CB A, then A to D. So that is 12, the shortest path. Okay, C to 5 to 7 7 12. The largest possible integer of the x, largest possible integer with at least one shortest path between some pair of the vertices will contain the edge with a weight x is given. So x is connected to C and D. Okay, C and D. So here the shortest path from C to D is weight 12. Okay, C to D is weight 12. So here the value is x here. So how we can find what are the C to D here? If you go from this 8, 10, 18, A to C, C to A to B, then okay. Or if you go from okay, here you won't get like so this is the way. C to B, then B to A, then A to D. Okay, so the weight is 12. Okay, the largest possible integer value of x for which at least one shortest path between the same pair of vertices, that contain the edge with weight x. Weight x is 12. Okay, so the answer is 12. Answer is 12 with the same vertices C and D. How we can connect? So C to D is same vertex. So X is connected to CD, right? With the same vertices. So 12 will get. Then the breadth first search is started on a binary tree beginning from the root vertex. There is a vertex t at a distance 4 from the root. If t is the nth vertex in the binary in this breadth first search travel, then maximum possible value of n is. So breadth first search that on a binary tree beginning from the root vertex. So there is a vertex t at a distance 4 from the root. At a distance 4 from the root. If t is the nth vertex in this breadth first search traversal, then maximum possible value of n is 31. So here vertex starts at a distance of 4 from the root. Distance is 4. From distance 1, the maximum possible value is distance 1. The maximum value is 3. Similarly, for distance 2, the maximum value is 7. From distance 1, the maximum value is 3. From distance 2, from this distance to maximum value is 7 here. So maximum number of nodes is 2 raised to h plus 1 minus 1. So there is a formula to find the number of possible values. 2 raised to h plus 1, 2 raised to h plus 1 minus 1. So distance is 4, right? So 2 raised to h plus 1. So 2 raised to h plus 1 means h means 4. So 2 5 will get 2 raised to h plus 1 minus 1. So 2 raised to 4 plus 1 means 2 raised to 5. 5 means 2 raised to 5 means 32. 32 minus 1. So that is 31. So for distance 4, the maximum possible node will be 31 and minimum will be 16. Minimum will be 16. So maximum will be 31. The maximum value will be possible value will be 16. 2 raised to h plus 1 minus 1. The next question, the n items are stored in a sorted doubly linked list. For delete in a doubly linked list, for delete operation, a pointer is provided to the record to be deleted. To the record to be deleted, pointer is provided. For a decrease key operation, a pointer is provided to the record on which operation is to be performed. An algorithm that performs the following operation on the list in the order of theta of n delete or big O of log n insert, big O of log n insert, big O of log n find, then big O of n decrease key. So what is the time complexity of all these operations put together? So that is big O of n square. N items are to be stored in a sorted doubly linked list. For delete operation, pointer is to be provided to the record to be provided to the record to be deleted. So for doubly linked list in sorted, delete needs O of 1 time and insertion takes O of n times. Find it takes O of n time in doubly linked list. So decrease by it takes O of n time. So now the number of each operations performed is given. Finally, the total complexity. For delete operation, that is O of 1 time into O of n. So that is O of n means we need to find also. So O of n into O of log n. So O of n log n. Okay, so the decrease key means O of n into O of n. O of n square. So overall the time complexity for this doubly linked list operation, this is O of n square. The time complexity of all these operations are put together, we get like delete, find, insert, decrease key, will get O of n square. The next question, a complete binary min heap is made by including each integer, that is 1 to 2023 exactly once. The including the each integer from 1 to 1023 exactly once. The depth of the node in the heap is the length of the path from root to the heap to that node. So the root is at the depth 0, the maximum depth at which integer 9 can appear, that is 8. The maximum that depth that integer 9 can appear, so that is 8. This is not possible because it violates the property of complete binary tree. We have the range 0 to 1023 elements. So here the depth is for ninth element is 8. 0, 1, the depth 0, depth 1, depth 2 till depth k. So that is 2 raised to 0, 2 raised to 1. So 2 raised to is equal to 1023. And we after this, okay, using this formula in the GP, okay, we'll get 2 raised to k plus 1 equal to 1023. So the level 9 means the depth is 8. The first is depth 0, so depth 8. Actually we have 1023 elements. We can achieve completely binary mean heap of depth 9, so which would cover 1023 elements, but the maximum depth of the node 9 can be only 8. The maximum depth is 8. The number of ways in which the number 1 2 3 4 5 6 can be inserted in empty binary search tree such that resulting tree of height is 6. The height of the tree with single node is 0, that is 64. Okay, so to get the height of 6, every level should contain only one node. So to get such a tree at each level, we should have either maximum minimum element from the remaining numbers till that level. So binary search tree possible is for first level 2 nodes maximum or minimum, second level 2, third level 2, fourth 5 6 7 2 level. Okay, so total 6, 2 raised to 6 into, and but entry level, for every level there should be only contain one node. Okay, so 6, 2 raised to 6, so that is 64. The height of the tree with single node is 0. Okay, so 2 raised to 6, that is 64.